Hi, everyone. Welcome back. So in this lesson, we're going to be talking about functional groups, intermolecular forces, but really just introducing the initial set of functional groups that might be attached to a hydrocarbon. So when we talk about functional groups, what we're really meaning is kind of any other set of atoms apart from carbon and hydrogen that might be attached to a carbon and hydrogen chain. So oxygen, nitrogen, halogens, sulfur. All of these, when they bond to carbon, they are either a weaker bond with the carbon or they introduce an element of electronic density that makes the whole thing just more reactive. So when we talk about functional groups, what we're really meaning is areas where chemistry is more likely to occur. So something that's more reactive than just the basic carbon and hydrogen chain. So usually when we talk about these or when we show them, there's just in general terms, we might include the backbone just as an R. So if you ever see me write like an R with a subscript 1 or 2, what it really means is just the rest of the carbon chain or the rest of the molecule. X, though, is going to be our first functional group. So X, when we write that, is to indicate that there's, whoops, too much, that there's some kind of halide group attached to it. So the functional group, when we write it, if it's attached to, say, an R chain, just as an X, where X is going to be equal to chlorine, iodine, fluorine, bromine, anywhere down that list, okay? So all of these are just a little bit more reactive, and we know that they produce, if they're going to ionize into water, say chloride ion or the bromide ion, is quite stable by itself. So anything that can release from the carbon backbone and become stable by itself, say in the solution, is just going to be more reactive than, say, a couple of stray carbons and hydrogens. So already we've got a group where there's just more likely to have some chemistry happen to it. And quite simply, it's just attaching on one of the halide groups. So if we were going to draw, it doesn't matter, just a generic kind of organic molecule, we would show it just by writing in whatever element is attached, okay? So it's that easy. Okay. So next functional group that we want to introduce is a quite an important one. So the alcohols. Alcohol isn't just one molecule, it's a whole group of molecules. Anything that has the functional group with a hydroxy on it. So anything where we're attaching an OH group on. So if we did our same kind of generic molecule, we might see an OH like that. Okay, so these are made by, as it shows, replacing one hydrogen atom with a hydroxide. Remembering that oxygen has to have 2 bonds, so it's really just, if we wanted to show that even more specifically, we could draw on an O with an H on another bond. Okay, so we've got the 2 bonds there, the 2 lone pairs for oxygen. So we still see that oxygen is a sp3 hybridized because it has 1, 2, 3, 4 areas of electron density coming off of it, and attached onto the carbon backbone. So it's that OH group that makes things an alcohol, and we show it just by changing the suffix from, so this would be a 1, 2, 3, 4, 5, so a 2-pentene. So this would now be so now the alcohol would take dominance over the double bonded carbon. So this would be a 1, 2, 3, so a 3 or a pent 3-ene 2-ol, if you like, where we're giving dominance to the alcohol and showing that it's on the second group. So each carbon atom in this drawing, in this ethanol, okay, so this is the one that's fine, say, to drink. If we go to methanol, that'll blind you. isopropyl alcohol or isopropanol, also not good to drink. Okay. Ethanol, it's not the worst. Every carbon atom here we can see is still sp3 hybridized, and the oxygen too, because it has the two sets of lone pairs on it, is also sp3 hybridized. So when we talk about the alcohol group or the hydroxide group being very polar, it means that there's a lot of pull and electron density up towards the oxygen. So again, like with the halide, we're getting a concentration of electronic density, well, where these two lone pairs are, right? Around that oxygen that really doesn't exist anywhere else in the molecule. And so because we have that concentration of electronic density, it's going to make it a lot more reactive. So this site is where chemistry is likely to happen for this molecule. Again, why we're calling it a functional group at all. Okay, so moving on to the next one. Oh, so just naming for it. Okay, so number of carbon atoms in the parent chain is still the root word. And like kind of I demonstrated there earlier, if the functional group's not on the first carbon of the chain, we use that carbon number to identify its placement. Okay, so first example that we have there, just one carbon. So it's meth methanol, right? So this is the one carbon and then OL ending for the alcohol. That second group, so this is a carbon here. It's just not written down, right? So we have 1, 2, 3 carbons. So that's prop. Because it's connected on the second one, we can either say 2-propanol or isopropanol. That should be NOL. Okay, isopropanol. Here we have the benzene group with one replaced hydrogen as the hydroxide. So this could either be benzenol. Okay, so that's the benzene with an OL. Or we already said that this could be called a phenyl group. And so it's also called phenol, which is a more traditional, and it's also an accepted name. So you'll see phenol used. And the existence of this oxygen here, pulling the electron density away from the benzene ring, makes this side just slightly more positive. So we might be able to get some chemistry happening on this side too. And so the existence of one substituent on this benzene ring changes the reactivity of other points on the ring. That'll become important if you do stick around with organic chemistry. Especially if you want to think about energetic materials and explosives. Phenol is an important starting molecule to start hanging some nitro groups off of this for any kind of explosive, really. Not any kind, but some of the major organic explosives. Okay, so here we have 1, 2 carbons. So we know this is going to be an eth as a root word. So this can be an ethane, 1, 2, and now we have 2 alcohols on it, so it'd be a diol. Or I'm sure you've heard about this. It's also called ethylene glycol, which is the more common name for it. But obviously, the ethylene, there's no double bond in here, so that can be not consistent with our other naming. And glycol, where's the glycol here? What does that even mean? So glycol, again, is a more traditional, older way of talking about it. The gly actually comes from the root Greek word for sweet, for sweetness. And the OL, again, just recognizes that it's an alcohol. So as say an engine coolant, some ethylene glycol, you might have heard that it can be toxic to animals, and you don't want to leave it around where cats, say, can lick it up because it tastes sweet. So that's where the gly part comes in. But again, it's not our acknowledged systematic way of naming things so that we know what exactly molecule we're talking about. Okay, and this last one here, So again, we've got 1, 2, 3 carbons. So this would be a prop as a root word, okay? But now we've got 1, 2, 3, 1, 2, 3, and there's a triol. So how do we connect all of this together? The easiest thing to do is just to say propane, 1, 2, 3 triol. It's pronounceable that way. And this, again, is systematic in a way that is perfectly acceptable. You probably have also heard about this as glycerol or glycerin, which again is not a systematic name, but it is a way that's quite commonly talked about. So glycerine, it's in your hand sanitizers just as a gelling agent. It's up there. Okay, ethers. Ethers, you'll kind of see a trend as we go through these things. So the first one, okay, well, the very first one was the halides, but now here we're talking about alcohols where we have just an O connecting to an H group or a hydrogen. What happens if we replace that hydrogen with more carbons and say more of a carbon chain? We want to have a way of talking about this. Obviously, it's different from an alcohol because now it's going to have different reactivity because of that carbon. And this is an ether, okay? So this would be where we have some carbon chain going through an oxygen onto some other carbon chain. Okay, so this is like it says, an oxygen bound to 2 alkyl or aryl groups, so either non-aromatic or aromatic groups, but just sets of carbons. So the oxygen still has to have 2 bonds. So in that sense, it's like an alcohol, but that's kind of where that sense ends. So these, if we're naming it, we just say the 2 alkyl or aryl groups on the oxygen. So we just name each of the groups and then write ether after it. The oxygen atom on this, let's check it out. We still have 2 bonds, 2 sets of lone pairs. So it's still sp3 hybridized. So how are we going to call this? So we'll call it 2 groups. So we've got a methyl group and a methyl group. So we can write it as dimethyl ether. We'll just write down ether afterwards. Because it's a dimethyl, there's really no confusion about where that rests or which one we're going to name first. Where we start to pick up problems is say, okay, this is an ethyl group. So right here we have ethyl and 1, 2, 3, 4 carbons over here. So this is a butyl group. Which one goes first in here? So like other groups before, we've just said, well, whichever one has the lowest letter, we'll just write them alphabetically. So this would be a butyl, ethyl, and again, we just write down ether. Okay, so there's no other way that we could draw this, just knowing, okay, there's a butyl group, there's an ethyl group, and it is an ether that would come up with a different molecule shape than that. Of course, here we've got the same number of carbons, so still 1, 2 on this side, still 1, 2 carbons on that side, 1, 2, 3, 4 carbons on the other side. So still a butyl, but we see that they're connected differently, right? So this, if it were a propane, we would say isopropyl, or if it was one of these carbons was connected in a chain like that, we would have a different name for it. So that we've seen it as isobutyl. But when all of the carbons are connected onto one, for a butyl group like this, it's called tert-butyl. Tert-butyl. And then the rest is the same, ethyl ether. Okay. This can also be a case where we'll see, just like we had the alcohol group, if it's not taking the dominant role in the molecule, we can call it a hydroxy. We'll see that there are other groups that take the last name. Like here, the ether is the most important functional group on the chain, so it gets to take the naming of it. But there are cases where the ether isn't the most important, and so we have to know how to name that as well. So if it's just another side chain, say, okay, over here we're going to have, I'm going to label it as a Y, because it's just going to be some functional group that is more reactive than the ether. But we also have an ether group on it. So in this case, instead of hydroxy, we're going to, where we have hydrogen, oxygen, we're going to call whatever the group is with an oxy. So if this is 2 carbons, this would be ethoxy. If it was 1 carbon, it would be methoxy. That's X, Y, okay. We could have butoxy. Okay, tert butoxy, and it just carries on like that. Okay, so that's the naming convention for the ether. Ethers are often quite like fruity smelling. They'll show up in flavorings like that. They're generally fine. Aldehydes. So now we're starting to get into something that's quite a lot more reactive. So if we have a double bonded oxygen on the end of the chain, so the functional group we're looking at here would be coming off of R, the generic chain, to a carbon, then oxygen, and then the 4th bond on the carbon is just to another hydrogen. So this is our aldehyde group. You might think you've heard it before us say like formaldehyde. So we'll actually see that a little bit later on. Excuse me. So aldehydes have a carbon atom bonded to a hydrogen and double bonded to an oxygen. So this carbon-oxygen group, this right here, this is called a carboxy, or a carboxyl group, or more. I want to erase it. I'll just write it down on the end here. It's also called a carbonyl. Carbonyl. Okay, so you'll see it written like that. When we're thinking of naming aldehydes, instead of an OL that we had for the alcohol, we have the ending AL. So as opposed to, say, calling something formaldehyde, well, actually, this isn't formaldehyde, this image here. It's a little bit misleading. If we wanted to draw formaldehyde, we would call it methanol, okay? And it would just be 1 carbon, double bonded to an oxygen. And there's the aldehyde group, and the R group is just going to be a hydrogen because there's only 1 carbon in that chain. Okay, so this would be formaldehyde. We've seen that shape before when we've been talking about chemical weapons. So that kind of reactive group where we've got 2 chlorines replacing the 2 hydrogens, and this was a phosgene as a chemical weapon, has the same shape as a formaldehyde, but obviously is, or a methanol, but is a lot more reactive and a lot more dangerous. So let's go back up to this picture and see what it was called. So we have 1, 2 carbons, so this should be eth. And then to put on the aldehyde group, just takes the AL, so ethanol. 2-methyl-butanol, so breaking it down, we still have the bute, so it's going to be 1, 2, 3, 4 carbons on the main chain. See that it's going to be an aldehyde functional group, so we can take that number 1 carbon and make sure that we put the formaldehyde on it, and it's a 2-methyl. So this would be 1 because it's where the functional group is. It automatically gets the 1. 2, 3, 4. So it's a 2-methyl. So on that 2nd carbon, we add in the methyl group. Okay. And so, like with all the rest of these, it's just a matter of taking the word, breaking it down by parts, seeing where the parent chain is, the functional group, any side chains, and drawing it piece by piece. Okay, so that is the aldehydes. For ketones, the functional group, and again, you can see that we're staying consistent with the kind of the way it's rolling out. So the last one we had, our R group was going to a carbon that's double bonded to an oxygen that went to just a hydrogen. Now that carbon is going to bond through to a different carbon side chain. So these have carbon atoms double bonded to an oxygen and bound to two other carbon atoms. So a carbonyl group, so this is the carbonyl, between two other carbon chains, okay? So to add, to name a ketone, we just add an "-one" on the end of it. Placing the number in front of the name to designate the carbon of the ketone group, okay? So we'll get to some examples. First, we want to mention that the carbon atom, so we've got 1, 2, 3 areas of electronic density. So this only is sp2 hybridized. The oxygen atom, so it's got 1, 2, 3 areas of carbon or electronic density. So same thing, now it's sp2 hybridized on double bonded oxygen. Okay, so if we were going to name, say, this guy, so we could call it acetone because that is the traditional name for it. But it's not the systematic name because, again, if you don't know what acetone is, you're not going to be able to get there from just the word acetone. So we see there's 3 carbons. So this is going to be, we know there's going to be prop in there somewhere. And to designate which one it is, actually, it can't be on either of these end groups because then it would be an aldehyde, right? So we could just call it propanone. Or to be perfectly clear, 2-propanone, but there really isn't an option here. Same thing if we went to, say, 1, 2, 3, 4, butanone. Could we have this on any other carbon, and would it show up as the same name? No, because if we put it over here on this carbon instead of that one, it would still be the second carbon because we're going to give the ketone dominance when we're numbering the carbons, right? So it'd either be here or on one of the end groups, and if the double bonded oxygen is on an end group, then it would be an aldehyde and not a ketone. So this is still the only option, but we'd still, I guess, call it 2-butanone. As soon as we get up to, say, pentanone, then we'd have to really number which one it is because it won't be clear from the rules of the functional groups themselves. What else do I want to say there? The only one that I've ever heard of kind of in an industrial way is as a cleaner solvent, so methyl ethyl ketone. So that would be what we would have called 2-butanone in the past. So here's the methyl group, there's the ethyl group, and there's the ketone in the middle. So methyl ethyl ketone. Now the more correct way would just be to say 2-butanone. Okay, so the last functional group I'm going to talk about in this video is the carboxylic acids. So here we're taking the same idea as the aldehydes and the ketones, just to the next kind of evolution of it. So a carbon with a double bonded oxygen, and now instead of going to either a hydrogen or another carbon chain, we're going to add an alcohol onto it. So here we have a functional group inside of a functional group, making the whole thing quite a lot more reactive, and it's called a carboxylic acid. So there's the carboxyl, you see, or the carbonyl. And it's called an acid because this hydrogen is really quite loosely held, because if we drop it, we can have an oxygen and another oxygen, and we can share that negative charge that would be created if we say if this hydrogen just is removed and there'd be a negative charge left behind, can be shared between the two oxygens. So that's quite stable. And so this functional group is quite acidic. what do we say? So we have carbon atom double bonded to an oxygen atom, the carbonyl, and the oxygen atom of the hydroxide group. Okay, so that's everything I just said. Naming the thing, we just add oic acid onto the end of the alkane name. So we don't say something something carboxylic acid in general. If it's easier to do, we would just add the something oic acid. So in this first case, only one carbon in the chain, so it gets methanoic acid. Just like that. Here, 2 carbons, so 1, 2 carbons, so this would be ethanoic acid. Here instead we've got a benzene group, so we can call this benzenoic acid. And this monster down here. Okay, so I won't even try to get you to name this thing systematically. But I mean, we can try. So here's, this would be 1, 2, 3, 4, 5. Everything's symmetrical, so it really doesn't matter which way we number it. So here we have an alcohol group on the number 3 carbon, and that's not going to take priority over all of these carboxyl groups. So we'd start off with that as a side chain, so we can write 3 hydroxy. And this is a pentane. And then we've got 3 carboxylic acids. So let's just write 1, 3, 5. Tri. And here's an example where we just write carboxylic acid. Just because, what will we write? Trioic acid. Just write 3 hydroxy pentane 1,3,5 tricarboxylic acid, or if it's slightly easier to write, just citric acid. So that's citric acid. Whenever we're looking for citric acid, or thinking about it as a flavoring, or like even as a vitamin C, that's more or less what we're looking at. Why do we call it an antioxidant agent? Well, look at how easily this thing is willing to be oxidized. So it can quite easily give up any of these hydrogens, or at least these ones on the carboxylic groups. So any oxidizing agent, so something that itself wants to be reduced, that's looking to pick up hydrogens from your the molecules in your cells that would lead to disease or aging. This molecule provides a bunch of pretty easy to access hydrogens, and our body can metabolize this thing also quite easily. So that's where the benefit comes in. Okay, so that's where we're going to leave it off. In the next video, we're going to visit what happens when we react, say, this carboxylic acid with a weak base or with any kind of base, and turn it into, say, soap. Okay. Last thing, I guess, you'll just also see this written as COOH, just as a shorthand. But that's where we'll leave it off. Okay, so we'll talk to you next time about carboxylic acid salts and soaps, and maybe how they have any kind of effect on other molecules. Okay, so we'll see you then. Thanks as always for listening. So long for now.